So when we're testing claims about a mean, the good news again is that I want to emphasize what you're going to be doing. So keep it simple. I want you to first state the parameters. In this situation, it will be u equals the true mean, blah, 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 blah. Be wordy here, okay? Requirements, SRS, we'll either put stated or assumed. If the population is normal, we'll say stated, or, and it's greater than 30, central theorem kicks in, we have normality, or both, or we can check box and whisker plot, should have no outliers, and a normal probability plot should be linear. Okay, and so when you do check these, I will want to sketch. That doesn't mean we're making it up. It just means I'm not making you graph it to the nth degree on that. Okay, so that's the P, the R. Once you have this, we run the test. When I do the test, we will have a null hypothesis, an alternative hypothesis. The null will be mu is equal to some claim. Alternatively, either not equal to, less than, or greater than. Remember, not equal to is a two-tail test. We double the p-value. Less than is a left-tail test. And greater than is a right-tail test. Make sure you list here the test statistic. For most of these, since sigma is unknown, we will do t. If you do t, you will also get the p-value. You also get alpha, but you must include the degrees of freedom on any t test. And that is if sigma is unknown. If sigma is known, we will run a z-test, p-value, alpha, no degrees of freedom required, because the z does not change depending on the sample size. Okay? And based on this, we'll write a conclusion. If the p-value is less than, reject, null, conclude the alternative. I'll be a little wordier with that. If the p-value is greater than alpha, fail to reject. So that's the short version of what I've already gone over with PRTC. The hypothesis process is the same here. 40 subjects follow the Weight Watchers diet for a year. The weight changes are summarized by these statistics. We have a mean, an X bar, the standard deviation, a 0.01 significance level. What is that? They've given us an alpha. So we're not going to use 0.05. They told us what to do. And test that the diet has no effect. Okay? So let's start with, what's the parameter? Well, we're dealing with a mean. So mu is equal to the average, true average what? Weight change using Weight Watchers. Requirements, since this is the mean, still check SRS. Did it say that they got those 40 subjects randomly? No. So it will be assumed. How do we get normality? Did it say that it's normal? No. Then I need a sample that is greater than 30. good news is N is 40, right? So central limit theorem kicks in, we got normality. T, we will do a 1 sample. Is it a T or a Z? Most of these are pretty much going to be t-tests. Why? This is not sigma, this is S. Okay? When I run that, I need the hypotheses. The null hypothesis is that mu is equal to some claim. Well, we didn't really get any numbers. This is a little crazy. But what do we consider if a diet is effective? What should your weight change be? Right? Well, your weight change should be negative, meaning you lose weight. What does it mean if it's not effective? Well, either you don't have any weight change or you gain weight. That's a sucky diet, right? So no change would mean that the average weight change would be 0. Alternatively, if the diet has no effect, then what we're going to do is try to prove its no effect is 0. I think that this leaves it open to not equal to show that the diet has an effect. I wouldn't mark you off for this, but I think this is kind of a lame way of running this test because I don't care whether the diet's just different than 0. I want to know that I'm not gaining weight with this diet. I want to prove that it's less than 0. So the wording no effect, if you put not equal to, I'd give it to you because that's technically we're proving that there is a change. It doesn't say greater than or less than. But I would argue that for a diet to be effective, you would want to lose weight. Okay? Not an A-basket issue here. I think we're ready to run the test. So let's see. In the menu, statistics, tests. This one would be a 1 sample t-test, just labeled as a t-test. We have statistics. Data means a list of data. Statistics means we actually have these statistics. The mu naught, what is the claim? No weight change. What did we see? We saw negative 6.6 pounds. We saw a standard deviation of 10.8. And a sample size of 40. Alternatively, we wanted to prove the diet was effective, losing weight. All right, so negative 3.865. P-value would be 0.0002. Alpha, 0.01. And since we're doing a t, do not forget, and I didn't list it here, but the degrees of freedom. So you need to put the degrees of freedom. Since the sample size was 40, you would put 39. Based on this, we have a conclusion. Since the p-value is, well, it's lower than alpha, right? We would reject the null hypothesis that mu equals 0, that the average weight gain is 0, and conclude that mu is less than 0. Means what? The diet works. Most diets do work. The problem is people get off the diet and then they start doing bad habits again, right? But this basically proves that there was a significant difference. This would not occur by chance. These people lost weight. Okay? If you would have done a not equal to, what it would have done is made it a two-tailed test, so the p-value would have been doubled, and we still would have had the same conclusion. Okay? So that wouldn't have been the end of the world. But I think the argument here is to show the diet is effective. I would say not, or less than 0. If you did a not equal to, your p-value would be different. In this example, I don't think I'd penalize you for it. Okay? I do want to say real quick, what if we knew that sigma was actually 10.8? What if that was the actual standard deviation of like all diets that ever occur? What if we knew that, right? Well, then instead of, first of all, the requirements would be the same. But instead of a t-test, we would do a one-sample z-test. The hypotheses will still be the same. This score actually will still be the same. So I'll show you when we run it. Menu, probability, nope. Where are we at? Statistics, tests. And at the very top, it would be a z-test. So the same claim of 0, but I said, what if that had been the true standard deviation of 10.8? And we had negative 6.6. And a sample size of 40. And I'd still argue for less than. Well, now our z-score is actually the same number, because the formula is the same for z and t, it's just whether you know sigma or s. So negative 3.865. But notice what happens to the p-value. Instead of being 0.002, it is 0.00056. That's a much lower p-value, right? We still would list the alpha. We would not need degrees of freedom because the z doesn't change depending on the sample size. But basically, the conclusion would be the same. What I'm wanting you to see is that basically using a t-test basically makes it harder to reject. It makes the p-value larger. Versus if I use a z-test, the p-value is lower. But we don't just use the z-test just because we feel like using it. We can only do it if they give us the sigma. But basically, what the t-test does is, remember, it gives us a distribution that's just wider. So it allows for more error. So it makes it harder to reject. Either way, these are significant results. But I just want you to see. So I will, on the quiz, have a question where I give you sigma. I will want you to run a z-test there. World's smallest mammal is a bumblebee bat. Listed below are the weight in grams from a sample of these bats. Assuming the weights of all bats are normally distributed, use a 0.05 significance level to test the claim that these bats are from the same population with a known mean of 1.8. Alright, so we have 0.05 significance level. That would be our alpha. We have a known mean, so this would be a claim. And we want to see if these bats differ. So do me a favor, take some time. If you need to pause this, you can. Type all this into A. What is our P? Well, mu is going to be the true average weight of the bats. And specifically, we're not doing pounds, we're doing grams. These are some tiny bats. Okay, think like the size of a butterfly, tiny bats. Our requirements: data must be collected what? It said sample of the bats, didn't say random. So I'm going to put SRS must be assumed. How do we get morality? Well, unfortunately, what? There's 3, 6, 9, 12, 15 bats here. So I don't know the central limit theorem. N equals 15. Uh-oh, that's not greater than 30, right? Well, if you type this in, I have it right here, typed them in and I named it bat, you can actually check normality, right? You can go and add a graph and check the bats. This isn't looking promising. I can look at a histogram, though that's my least favorite, but still looks slightly skewed to the right. What I really would like to see is a box plot. There should be no outliers. Uh-oh, there's 2 outliers. And this should be linear. And it's got too much like points that's kind of falling away. But this doesn't look horrible. But the big issue is the outliers. Okay. So you could sketch these. Two outliers. And then you could say, but, you know, this looked okay. But hopefully some of you are looking at me going, but you didn't need to do this anyway. Why? Because none of this ends up mattering because they told me that it was normally distributed. So the normality is going to be given to us. So what will happen is people will do this question and they'll do these diagrams and it's not a bad idea. But then they'll say, normality is not met. Don't run the test. And I'll say, I disagree. They told you it was normal. So if you choose not to run the test, even when you should, you basically thrown away a bunch of points. You're going to get like 2 points out of 5. You should always run the test. And then if you think that the requirements were not met, then at the end say, but these are invalid. That's what I recommend. Because in case you made a mistake right here, if you weren't screaming at your screen, if you're going, aha, I don't have to run this test, you could be throwing away a lot of easy points. Okay? So this all is good. But in this situation, this was not necessary because the normality was given. All right, what test are we running? A one sample t test. Our hypotheses, mu is the null hypothesis is always equal to some claim. And we want to prove that these bats are potentially different. I don't care if they're bigger or smaller, but they want to say, I think they're the same. We just need to prove that they're different. If you run this as a greater than or as a less than, things are going to be off. You'll have the same t, you'll have a different p. I can keep track of that. But if you write the same conclusion, you can still get most of the points. But in this situation, if they want you to test the same, then your alternative should be not equal, okay? So once again, we have the data, so it's actually pretty easy to run this test. Menu, statistics, tests, a t-test with actual data this time. The claim was 1.8. My list of data is in A. Alternatively was not equal to, put the results in B. Shade is kind of nice because it shows a picture of it. You don't have to do that, but if you do that, it adds a little picture to show you. By the way, notice I did a not equal to and they shaded what? Not equal to is a two-tail test. They doubled the p-value there. But I'm going to go ahead and undo that because it makes it, I think I can do it. There we go. I'm going to undo it because I know that makes it hard to see. So if I run the test, and what was it, 1.8, and not equal to, there we go. Then basically I can get a more clear picture. I think it was 1.8. No, I'm messing up. All right. So our p-value, oh, this is a stinker here. It basically changed the width for that picture, so bugger. I think I can change the width here. There you go, bring it in. So maybe don't do the picture. But we have a t of negative 1.297. A p-value of 0.216. And alpha they specified at 0.05. And do not forget on the t, degrees of freedom. How many bats were there? Well, oh look, this one actually gives it. So don't forget that, 14. Based on this, we can write a conclusion. I am what percent? No, wrong test, right? Since the p-value is greater than alpha, we double check your notes. Get these phrases right. Don't mix these up. Fail to reject the null hypothesis. Fill in what the actual null hypothesis is. Period. Conclude nothing. We have insufficient evidence to reject. We have non-significant results. Okay? So basically, we haven't proven that these bats are any different. Even though they're from a different area, they potentially, doesn't mean they are the same. We've not proven that. We just don't have sufficient evidence to prove they're different. Advertisement, pizza shop claims. All right. Mu is equal to the average what? Pizza shop. Requirements. Data should be collected. It says a random selection. So I don't have to put assume this time. I will put that it was stated. How am I getting normality? Well, this time normality is not made. I can't do a bunch of diagrams because I don't have the original data. So I need a sample size greater than 30. And n is 36, which is greater than 30. So we have normality. How do I run the test? A one sample t test. Our null hypothesis is that the mean is equal to the claim. What was the claim? Well, they claimed less than 30 minutes, so the claim is going to be compared to 30 minutes. And alternatively, we want to see if we got supporting that it is less than 30 minutes. Let's run this test. I'm going to go back to a regular calculator page. So menu, statistics, tests, on the very top, a t-test. This time with statistics. Fill in the pieces. They said mu naught, what's the claim? What actual average time did we get? Well, we got 28.5 minutes as an average, right? Well, that's less. Is it significantly less? Standard deviation of 3.5. And a sample size of 36. And what were we trying to prove? Less than 30 minutes. Hit OK. What do we write down? The t, negative 2.57. P-value, 0.007. Degrees of freedom, 35. I don't know why I'm running this 6, I'm picking 5. And alpha, they wrote right here. Based on this, PRTC, since the p-value is less than alpha, we reject the null hypothesis that the mean is equal to 30 minutes and conclude the alternative, it's less than 30. This pizza shop's doing a good job. Harper's Index claims 23% of people in the U.S. are in favor of outlawing cigarettes. You decide to test this claim. Of the 200 people, 27% are in favor. What is the P? Mu is equal to the average. We have a problem, right? Hoping you catch this. This is why I have you do this at the beginning. In this question, we have a percentage. A percentage. This is not an average. This is a proportion question. So it's going to be the true proportion of U.S. people who are in favor of outlawing zeros. Okay, what are the requirements? Data should be collected randomly. Right there. That makes it what? Second, somebody's going to tell me that n is greater than 30. No. This is a proportion question. So what I need is I need at least 5 successes and 5 failures. They didn't tell me the successes and the failures, right? This right here is the claim. This right here is the p hat. So what we do is we take the n times p hat, 200, times 0.27, should be 54. 54 is greater than not 30. How many successes do we need? 5 successes and 5 failures. That means the other 146 failures also greater than 5. That gives us normality for a proportion. Not greater than 30, at least 5 successes and 5 failures. Keep them separated. What test are we running? One sample t-test? No, these are proportions, so a one proportion z-test. We can run a z-test on proportions because it's always perfectly normal as long as we have that normality met. I need a hypothesis, not mu. P is equal to the claim. Alternatively, P is, well, what did they say? Decide to test the claim, whether they are in favor. I would argue that this doesn't make a claim. I don't see greater than or less than. I'm not dealing with a diet. So if there's no greater than or less than implied, do a not equal to. Two-tail test. That should be enough to run this test. Menu, statistics, tests. Don't do these two. These two are for means. A one proportion z-test. Our claim was, what was it, 23%? We saw 54 successes out of 200. I got those numbers right here. We used it, 54 out of 200. Our alternative is not equal to. What do we write down? Why did it? I don't know what just happened. I'll have to try it again. One proportion z-test, 0.23. Make sure I'm not crazy here. There you go. We had 54 out of 200. And this time I'm going to hit enter and see if that helps. There we go. So z, p-value, z is 1.344. P-value is pretty high on that one. 0.179. With an alpha not given. So we'll use. And based on this, our conclusion that p-value is greater than alpha, so we say since the p-value greater than alpha, we fail to reject the claim that p equals 0.23. Conclude nothing. Insufficient evidence. Insignificant. So just be careful. I just wanted to throw one more of those in because on the actual test, they'll be switching back and forth. Used car dealer. All right, so let's see. P. We're dealing with a mean price. Of 2002 Ford F-150 SuperCat. Okay? Requirements. Data must be collected randomly, SRS. Random sample, right there, means that it was stated. How do I get normality? 14 is not greater than 30. I don't have normality. See, normality is not given. And n is not greater than 30. So we do not have that means we're done. If I needed to run this test, I would, and I could get an answer to that. Oh, I freaking need to read. Hopefully you guys are yelling at your screen. I was all excited. This is where I would encourage you to read it, right? Read it, because normality was freaking given. Sorry about that. I was all excited. All right, the test. Null hypothesis. Mu is equal to, what was his claim? He said it's at least 18,800. You don't think that. U alternative, H alternative. To reject his claim. He says at least. So we got to think about this. If he wants to prove it's at least. If I want to reject that claim, we're going to try to prove less than. That will reject his claim. That's what I'm trying to disprove his claim. Honestly, I think the wording in this is a bit confusing. I will try to keep the wording clearer in the quizzes and the tests. Okay? Based on this, we can now run the test. Means are a t-test. We have statistics this time. Our claim is 18,800. The mean that we got was 18,000. That's our X bar. 1250, that's our S. 18,000. 1250. And we sampled, I think it was 14 cars? Yeah. And we're trying to prove, well, not equal to. We can't, there was no, oh, wait. Less than. We are trying to disprove something. Less than. You're okay? Hit okay. What do we need to write down? T, negative 2.395. P-value 0.016. Alpha was not given, so I'll use 0.05. Degrees of freedom, 14 vehicles minus 1, 13. Based on this, we conclude, since that p-value is less than alpha, we reject the null hypothesis, put it in words. We reject that the average car is $18,800 and conclude the alternative that it's less than 18,800. And last but not least, homeowners claim the mean speed of automobiles traveling on their street is greater than the speed limit of 35. Random sampling of 100 automobiles found 36. Is that significant enough away? The standard deviation of 4. Okay? So this right here, there's our claim. There's our sample size. This is from our sample. So it's a sample mean and a sample standard deviation. P. Mu is equal to, what are we interested in? The mean speed of the automobiles traveling on their street. What are the requirements for means? Data should be collected. This time it was stated. How do I get normality? Does it say it? I'm reading more carefully this time. No. So it's not stated. Is n greater than 30? Yeah, 100 is greater than 30. So we had normality by the essential limit theorem. We run a test, a 1 sample t test. Our hypotheses. Mu is equal to some claim. What was the claim? What are we trying to prove? People are speeding. They're going faster than 35. Based on all this, we can run a test. Menu, statistics, tests, t-test. We have the statistics. By the way, if you do this one and you go in there, it's going to ask for a list. That should stop you. Hit escape, change it to statistics. No big deal. The claim was 35. We got 36 with a standard deviation of, I lost it. Where did it go? 4. And a sample of, what do we have, 100 cars? And alternatively, we want to prove that people are speeding. T is 2.5. P-value. How about 0.007? Alpha was not stated, so 5%. And degrees of freedom, 100 minus 1, 99. Based on this, we can conclude, since p-value is less than alpha, we will reject the claim that mu equals 35 and conclude the alternative that it's greater than 35. Just for fun, what if this had been a z? Just because, like I said, that'll be on the test. When I go to my test, what if it had a z? What if that 4 had been the actual standard deviation? What if that 4 had actually been the true standard deviation? Notice the z numbers match. The p-value is a little different, but the conclusion would have been the same. So be careful. If you run the wrong test, just make sure you do everything else right. You're going to lose some points for that, okay? But make sure you do everything else right. But notice this really isn't that far off. We're off by like 1,000th. And the reason why is because the sample size is so large. The sample size was 100. And we talked about before that as the t-distribution, as the sample size gets bigger and bigger and bigger, it becomes more and more normal. It looks just like the normal distribution, okay? But still be careful. On this question, I would have wanted the t, so that would have been part of the credit. If you did on a z-test and a z and 6 and everything else was the same, you'd have lost a half point. So just be careful. I will be doing that on the quiz. There will be some where you have to do z, some where you have to do t. Be careful.